Math and Beats. This video, we're going to look at some limits of polynomial and rational functions, because we can. Let's get going. Alright, first thing we're going to do here is we're just going to consider this polynomial p of x right here, polynomial function, which is 8x cubed plus 5x squared plus 3x plus 4. We're also going to let a just be some arbitrary real number. And what we're asked to do is find a limit as x goes to a of p of x. So this polynomial, think about it first of all. Polynomials, if you can remember some pre-calculus, they're defined for all real numbers. And so what we would expect here is that this function's limit should be the value of the function. But in order to do so, to show it, we're going to use our limit laws to see how that works. So let's take a look here at this limit as x goes to a of p of x. Well, that's the same. Limit x goes to a, of course, of the function 8x cubed plus 5x squared plus 3x plus 4. Now, we have our limit laws. In this case, we have a sum of monomials being added together, which, of course, allows us to use the sum law. So we could write this as limit x goes to a of 8x cubed plus the limit as x goes to a 5x squared plus the limit as x goes to a of 3x, and finally plus the limit as x goes to a of 4. So there's our sum law. We could then take out the constant multiple from each of these as well and get 8 times the limit as x goes to a of x cubed plus 5 times the limit as x goes to a of x squared plus 3 times the limit x goes to a of x. And remember from a previous video, we saw that the limit of a constant is that constant. So limit as x goes to a of 4 is just 4. And now, so we just did a constant multiple rule for these limits because each of the individual limits do exist here. And so the last rule is we got x raised to some power in each of these. So remember that power rule for whole number powers allows us to write this as follows. 8 times the limit as x goes to a of x quantity cubed. Remember, limit of a function to a power is the limit of that function, quantity, to that power, assuming the limit exists in the first place. And for each of these, we have an x and an x and an x. Y equals x always has a limit that exists. So moving on, plus 5 times the limit x goes to a of x squared quantity. And then we just have that limit of x as x goes to a of 3. Now, this limit right there, again, y equals x. Limit's going to exist at any value of x. So that should just be a 3 times the a, and then plus that 4. And so finally you see, okay, we evaluate each of those limits as x goes to a of x. We just get a, so then we get 8a cubed plus 5a squared plus 3a plus 4. And notice that indeed, as we had suggested, this is the actual value of the function p here evaluated at a. So you can imagine doing this for any polynomial, and though it's not being proven, it's reasonable to conclude that in fact every polynomial function, when you take its limit as x goes to some real number a, is just the value of the function at that number a. Now, moreover, if you have two polynomial functions, let's call it p of x and q of x, if they're both polynomial functions, then if I take the ratio of p of x over q of x here, call it the function r of x, by definition, that's a rational function, right? Rational functions are ratios of polynomials. And we just saw that, oh, if I have a polynomial function and I want to take its limit as some real number a, just plug it into the function. And so here, because p of x and q of x are both polynomials, then we take the limit as x goes to a of this rational function, then we have a ratio of polynomials, and it allows us to use the quotient law for our limits. Thus, by our limit laws, specifically the quotient limit law, the limit as x goes to a of this rational function r of x should be the ratio of the limit as x goes to a of p of x divided by the limit as x goes to a of q of x. But again, they're both polynomials, so on top we just get the output value p of a, and in the denominator we get the output value q of a. Of course, that is assuming that the value of q at a is non-zero, because then we'd be dividing by 0. So that can happen. So that's always going to be true as long as the output value of q at a is non-zero. So we can kind of summarize these results, and that is, if you have two polynomial functions, p of x and q of x, and you have some real number, a, then what this says is, first part, part I, the limit as x goes to a of a polynomial function p of x is just the output value p at a, just the output of the polynomial at that location. And in part I, limit as x goes to a of the ratio of two polynomials, hence the limit as x goes to a of a rational function, is just the ratio of the outputs p of a over q of a for q of a non-zero. So some limits, like these, if we identify that we have a polynomial or a rational function, just plug in the value that x is approaching into the function, nothing else to do. Just being aware that the denominator for the second part should be non-zero at that location. So to wrap this short video up, we're just going to look at a couple of examples here. Find these limits. Well, look at the first one in part A. Limit as x goes to 2 of negative 4x cubed plus 6x squared plus 5x minus 3. We're just taking the limit as x goes to 2 of a cubic polynomial function. So all we're going to do is just literally plug in 2 to all the x values. We get negative 4 times 2 cubed plus 6 times 2 squared plus 5 times 2 minus 3. So we're just going to evaluate this. All right, 2 cubed is 8 times a negative 4 is a negative 32. And then 2 squared is 4 plus 6 is, or times 6 that is a plus 24 plus a 10 minus a 3. Negative 32 plus 24 is a negative 8 plus a 10 minus a 3. What do we get? 2 minus 3, which is negative 1. Of course, you can just plug that into the calculator as well. I don't have my calculator handy. So it's just a matter of, we've got a polynomial, we're taking its limit as x goes to some real number, plug that number into the function, boom, that's the limit. The second one, we have limit as x goes to 3 of a rational function now. Ratio of two quadratics. So we're going to just plug in 3 everywhere for x, as we had stated before. And if the denominator happens to be 0, well, then we got to play a different game. But let's just see if that happens or not. Plug in our x is 3 everywhere. All right, well, on top we got a 3 times 3 squared minus a 4 times 3 plus a 1. All divided by, plugging in 3, 5 times 3 squared plus a 2 times a 3 minus a 1. All right, 3 times 3 squared, that's 27, minus a 12 plus a 1, divided by 5 times 9, that's 45, plus a 6 minus a 1. And let's just add this stuff up. 27 minus 12 is a 15, plus a 1 on top. On bottom, 45 plus 6 is 51, minus a 1. So we get 16 over 50, which is the same as 8 over 25. And there you have it, right? So it's just a short video showing that, and it's reasonable to conclude this, that limits of polynomial and rational functions are just the according output values of those functions, but understanding that for the rational function, the denominator should be non-zero in order for us to do this. And that's the end of that video. So we can do this now, but we're not done with this kind of section of types of conversations on limits. What is going to follow this video is a video on how we can use algebraic techniques to find limits in particularly certain situations, as we're going to see. So next video to come. Till then, Math and Beats.